All right, I'm Sam. I'm here to give an introduction to the Crimson project, and then I'm going to talk a bit about what you can expect in Reef and what we've been working on generally. So the main driver of the Crimson project is that storage technologies are constantly driving towards ever higher numbers of IOPS. I keep not updating the slide, so this is actually low compared to what you can get now. We started off with hard disks when Ceph was first being created. That could maybe get you 150 IOPS. We got some super fast SSDs thereafter that could perhaps do 10,000, and then it's gotten worse since then. Modern NVMEs can push 1 million, no problem. But CPU throughput really hasn't kept pace. With the sort of 150 IOPS, a hard disk could get you could afford to spend perhaps 20 million cycles per I/O. With SSDs, 300,000. But with an NVMe device, only like 6,000, which is not many. That's few, in fact. So what we've gotten instead of additional single core speed is more cores. So Ceph's original architecture scales pretty well with multiple cores, but at the expense of a lot of latency. So what we're interested in is an architecture that allows us to exploit a lot of cores without requiring a lot of inter-core communication, and without requiring us to just assume that cores will magically get faster year over year, because that appears not to be true anymore. So here's a graphical representation of CPU usage in the OSD that I stole shamelessly from Kifu and Radek's presentation in Barcelona many years ago now. But the reality hasn't really changed. We can see several of the OSD's thread pools represented here. We've got the BlueStore finisher, FN anonymous. We've got the messenger thread pool, and we have the OSD op thread pool. So if we look at the request commit callback, because the callback needs to reach into PG structures, which are also used in the OSD op thread pool, we spend quite a bit of time acquiring locks here. And if we look in further to the nested PG callback, we see yet another lock, specifically over the state responsible for watch notify. And in most scenarios, it's not even used. You can also see that we spend quite a bit of time in the kernel TCP IP stack sending and receiving messages. So there is quite a bit of CPU overhead inherent in the classic OSD threading architecture. The Crimson project is meant to solve at least specifically the inter-thread communication and scheduling non-determinism component of this. At its core, the project has two major goals: minimize CPU overhead per I/O, as much as this architectural switch can, by reducing cross-core communication, copies, and context switches. And then secondarily, we want to exploit emerging storage technologies that are challenging to exploit with classic OSD, specifically ZNS and SMR technologies, as well as NVMe in general, due to the performance characteristics. So to that end, Crimson is a rewrite of the Ceph OSD daemon to address these goals. The goal here is to improve IOPS per core more than raw IOPS. Classic's actually very good at throughput if you give it enough CPU. The problem is that it's very expensive and that the latency becomes problematic for reasons I'll get into. So we want to reduce the per IOP cost in that way. So let's talk a bit about the classic OSD threading architecture. There are, broadly speaking, three major components of the OSD op processing pipeline. The pink box on either side is the messenger, where we receive messages from the outside world and then send them back out when we're done processing them. Middle here, we have the PG state responsible for operation ordering, recovery, peering, all that good stuff. And the object store here, which will generally be BlueStore, responsible for the actual I/O and on-disk transaction atomicity. So for a small unreplicated write, the client message is read off the wire by a messenger thread, which places it into the op queue. An OSD op thread pool thread and then picks up the message, creates a transaction, which it queues for BlueStore in yet another queue. BlueStore's KV sync thread then picks up the transaction along with everything else in the queue, synchronously waits for OXDB to commit the transaction, and then places the completion callback back in the finisher queue. A finisher thread then picks up the completion callback and queues the reply for the messenger thread to send. So each of these thread handoffs requires inter-thread coordination over the contents of a queue, and there's some non-determinism over whether the thread happens to be scheduled. Moreover, with PG state in particular, more than one of these threads may need to touch the internals of any PG, so there's some possibility that you can tend on the lock, even with a decent number of PGs. So by contrast, the goal with Crimson is to set things up so that this entire process happens in a single thread. And assuming you don't have to wait for I/O, it won't even block. So we do this by co-locating the portion of the object store, the PG, and the messenger that deal with any particular request all in the same thread. So the way this works is that rather than explicitly passing around callbacks, so to do this, Crimson uses a C++ library called SeaStore, developed for the ScyllaDB rewrite of the Cassandra implementation thing. It's effectively a user space scheduler that is capable of multiplexing a bunch of asynchronous operations on the same threads. So rather than having a bunch of thread pools, each of which have their own group of threads, each core gets one thread, and that thread multiplexes its own operations using an internal queue. And we try to minimize the degree to which operations need to bounce between cores. So rather than explicitly passing around callbacks, SeaStore's I/O interfaces are structured around futures. So if we look at this sort of comparison, on the left here we have what looks like a super simple synchronous sequence of operations. We read a request off the wire, which just blocks until it's done. We handle the request, same deal, just blocks until the I/O is done, and we send it back, which again blocks. On the right side, we have the sort of SeaStore version of this. We, in a loop, repeat, create a future, read request, and then we chain a callback, which handles the request, onto which we chain another callback, which sends the response. So if any of these things need to block, they simply return an unfinished future back up to the scheduler, which runs something else in the meantime. But if they don't need to block, it just runs to completion. Let's see. So the second major goal for Crimson is to exploit new emerging storage technologies like NVMe and ZNS. So SeaStore is the name of this object store. It is a new object store implementation designed natively for Crimson's threading and callback model. It avoids CPU-heavy metadata designs like RocksDB, and it is intended to exploit ZNS, which I'll get into now. So ZNS is a new NVMe specification that is intended to expose the fundamental reality of how Flash works. You can't actually modify a byte in the middle of a Flash page. You need to erase the entire page and then rewrite the whole page. The fact that drives give you the illusion of being able to perform that overwrite means that internally they have to implement what is effectively a log-structured file system. And that means garbage collection, which I'm sure we're all familiar with. So that tends to introduce a bunch of knock-on effects like latency non-determinism. You can't predict when the drive is going to do garbage collection and thus impact your client visible latency. And it means the application has no control over write amplification. So when you perform a write, you have no control over how many writes the drive actually needs to do to perform that write. And that's a problem for certain new Flash technologies like QLC because their write endurance is very, very poor relative to other technologies like TLC. So we don't really want to leave that up to the drive, particularly since the OSD is already a giant pile of code responsible for doing I/O. We would quite like to have control over that ourselves. So the ZNS specification kind of cuts out the middle FTL layer and leaves something very simple. In exchange, we don't get to do random overwrites anymore. The drive is divided into zones, which can only be open, written sequentially, closed, and released. So we have to restructure the entire rest of the object store layer to deal with that reality. As it happens, however, this write pattern is pretty good for conventional SSDs as well, because if you write like this, then the garbage collector has very little work to do. You don't tend to overwrite the same pages. Or when you do, you overwrite a whole bunch of them at the same time, so it gets to do a big release and doesn't have to rewrite the pages. So what is an object store? The term is super overloaded, and I very much regret retaining it for this purpose, but for the OSD internals point of view, object store is a C++ interface that provides a transactional interface to a flat object namespace. Object names are alphanumeric, they're strings, and they can be big because they are potentially controlled by users. So for RGW, for instance, if you store an S3 object, the name of the head of that object will be what you actually set. Like it's the actual object name you created in S3. This allows RGW to go directly to the object without having to go through an index. But in exchange, our internal metadata has to live with that reality. So we have to store these big names. Each object also contains, optionally, a key-to-value mapping that RGW uses for its bucket indexes, and CephFS uses for its directories. Let's see. We also support copy and write object clones. So you can create clones of an object, and as you mutate the head object, we're supposed to maintain the unmodified sub-ranges as shared blobs, so we don't blow up the storage space. And we support ordered listing of both the OMAP and object namespace. Object namespace is important because it's how we do both scrub and recovery. So that needs to be both correct and efficient because we use it during backfill. So at a super high level, SeaStore looks like this. There are sort of two sides to the extents we store. On the right side here, we have the LBA tree, which is stored by physical extent. Any address you have over there is the actual location on the actual disk where it actually is. On the left side of the tree is everything stored by logical address, which are the addresses stored on the right side of the tree. This lets us store all of the semantic data for like user visible stuff in an indirected address space, which allows us to move this stuff around without having to mess with the higher level structures. This is important because it allows us to do garbage collection, which is crucial for ZNS. And it allows us to do a tiering implementation and also copy and write clones, since it creates an easy place to do ref counting. So in a larger sense, the reason why we're doing an LBA indirection here, why we're paying this additional space overhead, is that when we do garbage collection, we need to do two things. Let's say we have this chain of references, A to B to C. Let's say these are nodes in a B tree that reference each other. So if we have to GC node C, we need to, and it's still live, of course, we need to find all of the incoming references, B in this case, and write out a transaction updating and dirtying those references as well as writing out the new C, because it's in a new place now. So if we were using physical addresses, this would be quite expensive. We would still need to find a way of finding the parent pointer B. So even if we did use direct references, we would still need some kind of back pointer system. Btrfs has something like this. It can be very complicated. And if this is, for instance, the B tree we use for OMAP, they're relatively low fan out because we have to store these like user stored keys. So we don't have that many keys in each B tree level. So it's a lot of write amplification, relatively speaking. By contrast, if we have an LBA tree, we simply need to update the logical address location of C prime, which would be an update to the LBA tree, which is very high fan out. So we have a high probability of hitting a node we've already mutated. So by the time we rewrite out that extent, we've hopefully mutated it multiple times. So we get a lot of locality that way. And as I mentioned before, it creates a natural place for doing subtree sharing for copy and write clones. And we can use it to do sparse mapping. So pretty much everything we write to SeaStore looks like this. There's a journal segment with a header, a set of deltas, which are logical changes to the extent. For something like a B tree node, this won't be byte range changes. It'll be something like insert key X or delete key Y. So the type of the extent can determines what the delta actually means. So we can be very compact in how we represent these. Then we have the actual, any extents we're rewriting, so logical and physical extents. So if our initial state is this extent D with extent E referencing it from the LBA tree, then if we want to update, or if we want to add node B to this tree under node D, we write out B. We also write out A, assuming that it requires a split or something that requires a new extent in the LBA tree. And then we write out deltas to their parents that indicate that they're now pointing at these new children. And for ZNS, we're particularly interested in trying to avoid needing to use direct addresses here. Because if you're using ZNS append, you don't necessarily know what address the write's going to end up at. So these internal references are relative to the record location. We figure it out on replay by looking at wherever the record actually showed up. Architecturally, it's divided into components above and below Transaction Manager. Transaction Manager supplies this like transactional interface in terms of logically addressed blocks that everything above it, the things that provide the things that the OSD actually cares about, uses. So we can do tiering and garbage collection for O nodes, OMAP B tree nodes, the actual data extents, and anything else we choose to add later, transparently without actually having to care about how those extents are implemented. And everything below that works simply in terms of these uninterpreted extents. recent work. The main theme for Reef for Crimson has been getting it to a place where it works, kind of. We want to get to a place where it's stable enough that users can start experimenting with it and giving us performance feedback and bugs that we won't simply go, well, yeah, that part isn't implemented yet. And I think we're basically there. A ton of work went into stabilizing the BlueStore versions of the RBD and Rados tests, at least a basic subset of them. We've created new tautology test suites, Crimson Rados, which should pass, and Crimson Rados Experimental, which doesn't yet, so that we can move tests from the one to the other as we fix the relevant bugs. And we're actually using the Crimson Rados suite to gate PR merges now, which is a super important step to making sure that we don't introduce regressions. The initial version of Crimson, because we were primarily interested in demonstrating an advantage in per core efficiency, didn't support multiple cores at all, because we didn't plan on any kind of architecture that would have interesting inter-core communication in the first place. But now that we've pretty much done that, we're adding multiple cores because we want to be able to use a lot of cores. So initial multi-reactor support has been merged. PGs get sort of deterministically split across the cores, and then they just live there forever. So once a PG is on a core, all IOs for that PG go there in the future, with appropriate message routing from the messenger over to the PG it's supposed to be at. And that should be the only network hop, or the only core hop you need to do. We've, I believe, merged all of the initial support for snapshots, including trimming, so that's super exciting. It's an important feature for RBD. Because we're interested in users actually using this now, it was very important to make sure that users do not accidentally use Crimson, because while we want users using it, we do not want anyone trusting actual data to it yet. If your cluster breaks, we'll be interested in learning why, but we probably won't help you fix it. So you have to set an experimental feature flag in the old classic Ceph version with a super long, annoying feature flag. And once a cluster has been tainted this way, it will not let you untaint it. So until you set this, it won't let a Crimson-OSD boot, and you have to tag each pool you want to be able to map onto a Crimson-OSD specifically, because there are a few features we don't support yet, like changing PG pool size, for instance. You can't change the number of PGs. And there's documentation for this, by the way. You don't have to memorize this slide. So the current status is we support RBD workloads and replicated pools. BlueStore and SeaStore backends both work, although the BlueStore backend is the one that we sort of expect to take a while to crash, whereas SeaStore I expect will crash quite quickly. And there's a strictly in-memory ScienStore if you're interested in doing performance testing on the top portion of the OSD. There is support for deployment via Ceph ADM, and vstart -- with Crimson will get you Crimson OSDs. So next steps. Now that we have a little bit of the tautology suite, the next step is to get all of it. We have Baton to thank, by the way, for the coverage we have so far. It's been great. It's fixed a ton of bugs. And the next pattern, or the next step, will be to get the entire rest of the suite except for the cache sharing stuff, which we probably won't port. We don't have scrub yet, which is very important, since if we are corrupting data, we probably won't notice. So it's very important that we get that done sooner rather than later. And there are additional steps for multi-core we need to do to improve the way the messenger behaves. And the big theme, now that we have some basic correctness, will be measuring and improving performance based on what those measurements say. Let's see. For SeaStore, same kind of deal, where you need to get to a place where SeaStore technically works so we can start iterating more quickly. And we're getting to that point. The Crimson Rados experimental suite has some SeaStore tests, and we can even complete an entire Rados API unit test, which is very exciting. Another major development theme is tiering. As I mentioned, we want to be able to combine the slower, cheaper storage with the faster, better storage. So we are adding internal infrastructure to allow extents to be moved transparently between the two portions. Metadata pretty much already supports that, so the goal here is really heuristics and an actual tiering agent that notices and moves stuff around as part of the garbage collection process. Performance in SeaStore will be a huge thing, although it'll be less measuring and improving and more simply rewriting the metadata structures that need to be rewritten as we get more mature. The LBA tree in particular is gaining a fairly sophisticated system for making sure it can do its traversals strictly in memory. And next steps will be more stability. getting tiering up to a place where you can actually use it in a real workload and we can start measuring it. We don't have snapshots yet, although a lot of the initial metadata support does exist. And multi-core reactor, or multi-core support, which will be very basic to begin with. It'll just basically create a bunch of little SeaStores, one for each core, and each PG gets stuck on its local SeaStore, and that's it. So that'll give us a really good performance prediction, and the only thing that won't quite fit is we'll need a way to like dynamically move space around. But we can do that later. It won't be in the fast path. So I think that's all I prepared. We have some time left if anyone wants to discuss or has questions. Thank you.
The tiering can that be used as a write cache, perhaps?
Yeah, both. Like I said, we're working on the heuristics now. The way the metadata was, the way I initially set up the metadata isn't particularly opinionated about it. It doesn't really care where the extents are. So we're trying to get to a place where the sort of tiering background agent is pluggable, and we can start testing a lot of different heuristics for how to do this. So the very first strategy that was implemented was everything goes into the fast tier, so it behaves as a write cache in that context. We're now adding the ability to promote cold extents up to the faster tier as they get read. And after that, it'll be a matter of measurement and finding more and more workloads to test and optimize for. That particular bit I expect will be a long iterative road. So if you have a workload you'd like it to work well on, testing.
That feature sounds really exciting, actually. It's like something like the ZFS, C2, and the Z-log, like can go onto fast flash.
Yeah.
Do you expect that since the beginning, since FileStore, you've had like 50 to 100 gigabyte SSDs and then spinning disk behind? Do you expect that kind of ratio to work with even the work in SeaStore?
So with FileStore, the only thing you could put on the faster device, if I recall correctly, was the journal. These days, BlueStore can put the write-ahead log and also the BlueFS partitions. Anyone who knows more about BlueStore than me, feel free to correct me. SeaStore is much less opinionated. It really doesn't care where the extents are. I expect we will iterate through a lot of different heuristics for where we want to put data, but I expect we can make some guesses. We'll probably want the whole LBA tree to be in fast storage, always. We will probably want most of the ONO tree to be in fast storage. But we actually have the option of identifying cold portions of the inode tree and demoting them if we want to. Like, we could create pool flags that make it so that some pools tend to have their portions of the ONO tree in fast or cold storage. Yeah, the sky's kind of the limit, which is good and bad. It means there's a ton of design space to explore, but yeah. So in short, I don't know. I think a lot will depend on the relative costs of those pieces of storage and what their relative performance properties are. And a component that wasn't really present in either FileStore or BlueStore errors, but will be going forward, is write endurance. So the coldest tier, if your coldest tier is a hard disk, you don't care, because hard disks have excellent write endurance. But if your coldest tier is QLC, then suddenly you care a lot about having enough fast tier, not so much to produce better performance, but to absorb the writes into the high mutation rate objects, because those writes would otherwise kill the colder tier. So I think that's going to be an interesting design space to explore.
What kind of back-end infrastructure could work? When you think about it, you have drives, then you could have partitions, you could have a file system. What can you actually put the SeaStore on?
Oh, it's going to be raw partitions. Yeah, or the whole disk, whatever. It expects a block device. If you give it a file, it'll be fine, but I can't think of an advantage. Except for development, obviously. If you're using development, yeah, you probably just make a big file.
Partition should be fine.
Yeah.
Will Crimson some kind of QoS scheduling, like what to prioritize recovery or client operations? Or
Yeah, we're going to port exactly the same thing we did in Classic over to begin with. It'll be a little, well, I say exactly, but the internal infrastructure in Crimson's a little different, so it'll be a little different. But I haven't done it yet, so this is not a promise, but my prediction is that I will end up preserving the same config values, and you would reasonably expect them to do pretty much the same thing.
mentioned the multi-core part that the placement group is attached to a core.
Yep.
So would it be better to disable hyperthreading on these machines to not attach a placement group to a not so performant core?
I don't know.
Okay.
It could go either way, right? It could be that that kind of task parallelism is actually great for this use case, or it's awful. It's hard to, a great deal depends on the hyperthreading implementation. If the portions of the core we care about have 2 copies, then it's probably better to use hyperthreading because you'll get better utilization of the core. But if we end up contending on resources on those logical cores, then bad, right? So I don't know. It could also be some kind of weird throughput latency trade-off where you get more latency by enabling hyperthreading, but you also enable the kinds of noisy neighbor issues that tend to produce latency tails. So it could be a trade-off. I would be curious as to what people find with different processors.
So Crimson's using a new programming paradigm, right? Promises features. I'm not an expert, but
Yep.
what's been the experience onboarding new developers?
It's a huge pain in the ass.
So is this going to be a problem going forward? Are you considering to simplify it somehow?
So the fundamental problem is that doing synchronous programming with threads is actually pretty ergonomic. Like, no one likes working with threading, obviously. It's more difficult to reason about. But to the extent that you're just using threads to multiplex a lot of synchronous I/O onto a core, it's super easy, really convenient. This is harder. You don't preserve your stack when you go from future chain to future chain. So you have to be much more deliberate about managing memory, and it's much easier to make mistakes. The good news is the new C++ standard has a coroutine concept that I'm genuinely hoping will make this much more tolerable. But the fact is, once you're trying to do higher performance stuff, you're trying to be very careful about allocations, and you're trying to be very careful about user space scheduling. Yeah, there's no way of doing this that's just straight up easy. So it is what it is.
I can tell that starting writing new code with Crimson is difficult, but once you already have a code base nearby to copy from, it's really just like any other coding, more or less.
Fair enough.
I have a question about SeaStore GNS. As far as I know, GNS has some restrictions such as zone size and multiple open zones. Do you have some issues related to RISC?
Yeah, that's a challenge. I've talked to a few different vendors, and there are a few different schools of thought on how many zones you're allowed to have open, how big the zones are, how big. Yeah, it's a bit of a Wild West situation. The backend driver is very primitive right now. I think it was only tested with like one variant. The goal probably is to address this in the backend driver. We do not expect to have very many zones open. We want a number of zones open that allows us to do what we need to do. And which is like 10, 16, something like that. It's a number low enough that I haven't heard any vendors say that that's a problem. Where it does become a problem is that's often not enough to saturate the device. So in those situations, we will probably set up the backend driver to map many zones to a single SeaStore segment, so you stripe. And that should work fine, I think. Does that make sense?
Does CNS allow you to provide independently F-data sync to different stripes you open? Meaning, when I have one block device, and I have one F-data sync that basically synchronizes all the data I stream into the device. If I have ZNS and open multiple stripes on the device, can I just get F-data sync to a single stripe? So I can still wait for the other to complete.
I can't remember how the interface works there. Sorry. Yeah, we can look at the spec later, though. Anyone else? Oh, go ahead.
What about what is it called? RAID controllers. We have customers, they love their enterprise giant RAID controller to attach to disks. And I always tell them, yeah, just turn it off and attach the disk directly, basically directly without the interference of a RAID controller to not mangle with SEP. What about Crimson? Is it,
Pretty much the same story. I mean, to the extent that the RAID controller provides a thing that improves throughput or latency or something, or allows us to do commits faster, maybe. But that was more of a thing with hard disks. The interesting component of a RAID controller there was more the battery back cache, right?
Yeah.
I don't know that I would voluntarily accept a RAID controller in between me and an NVMe device, though. That seems like unnecessary latency, but much depends on the details. So.
Yeah, this is something I try to convince some customers. Not later.
We on Crimson have some OMAP or key value store we have with all OSDs right now? Or,
Yeah. So everything I've discussed so far is a re-implementation of the protocol that already exists. The only feature we're discussing not carrying over is cache steering. I say that. The only big feature that we're that we're probably not carrying over is cache steering. I reserve the right to not carry something else over.
So the caching mechanism, does it require extra NVMEs? Can you use two to partition them and make read and write on one device?
I think you're asking, so let's say you have like 10 OSDs on a single machine. Can you take a single NVMe and divide it up so that each one gets a little piece of it?
Yes.
That's probably going to be the most common way to use it, yeah. It was traditional with FileStore to do that for journals, super traditional with BlueStore to do it with, yeah, so I do expect that'll be very popular.
Well, just note, because this seems like the right audience, regarding questions asked, I have a specific task about, talk tomorrow about this process of how we translate existing component in the classical OSD into a Crimson one. So if anyone curious about this process is invited to the talk tomorrow.
Which one is it?
From classical to the future.
Yes. All right, thanks.